Hi, everybody. Welcome to the talk on Creative Improvised Interaction with Generative Musical Systems. I'm Shlomo Dubnov, and this is a joint work with Gérard Assayag from IRCAM in France, Centre Pompidou, and Vignesh Gokul, also from UC San Diego. This is part of a larger project called REACH, human human-machine co-creativity, as sponsored by the European Research Council. So maybe before going into the technical details, let's have some examples about what is machine improvisation, or what are generative musical systems used for in live interactive mode. So this is the first example, an improvisation by Bernard Loubat. And please notice that we have the human performing on the piano, so you'll hear the piano sounds, and then there is a computer that adds other sounds to the performance, to the improvisation, and you can note the computer by more of a electronic sounds coming and are intermingled with his improvisation. So notice how slowly an interaction emerges, and how both the human and the machine create a joint piece. So yeah, let's take a listen. So just to give some background, some understanding of the setup, this is an improvised performance. The computer sounds are not pre-programmed. Everything is happening on the fly based on a generative mechanism that takes into account what the pianist is performing, and using patterns, frames, that phrases that it captures from the musician to create its own response, and this actually generates the whole interaction. And the next example is slightly different style and slightly different ways of working with interactive systems. So you have Remy Fox playing the saxophone, and the piano sounds are computer generated. Later on, as the performance evolves, also towards the end, you can listen to more and more freedom of expression of the computer, so I might say. So let's listen to this example. So maybe you've noticed that, towards the end, the more repetitive sounds the human performer provides, actually, it sort of creates the space for the computer to start generating its own phrases and create this sort of a human-computer dialogue. So this brings us to the motivation of the whole project. It's really around music improvisation with generative agents. And both the humans and the computer, the musicians and the agents, interact by through musical, basically, communication. They respond to music of each other. So to be able to create such an interaction, of course, one needs to be able to listen, to understand, musically speaking, what is going on, make some decisions, and generate. So definitely, the computer has the ability to listen, to learn something, create a style imitation, and generate. But to go a little bit, behind the scenes or under the hood and see what's going on, the models that the computer has are still in some sort of controlled, or they have a lot of parameters that the humans can help control. So in this performance example, you can see that when we have multiple models, and you can see this also displayed on the screen on the right, when the musician wants to switch from one type of music to another one, and doesn't let the computer basically take a random decision, he communicates this with the humans. So let's see this example. So as you have seen, the human gesture, the gesture from the musicians communicated to the operators of the generative system. And in some sense, we want to be able to overcome this and let the computer interact more freely with the musicians by also having longer term strategies, some policies that it learns, create an interaction, and have reinforcement signals going between the human and the machine to have this emergent co-creativity. So the overall agent architecture encompasses different aspects. Of course, the computer is listening, it's learning, it's creating models. It has a control signal that could be formed as a scenario. Of course, it can also generate its own scenarios on the fly, depending on the musical setting, the performance idea, and it has multiple models stored in its memory. So part of the goal, as I mentioned, is that the interaction through reinforcement is going to be a big part of the system. The way the computer learns and the way it can get the information about its own decisions to choose certain paths is at the core of the project. So one of the basic models here is so-called variable Markov oracle, which is a way to build a graph over a sound example. So the most simple model here is not necessarily using any deep learning. It's actually an explicit model where the system finds repetitions of sound segments and creates alternative continuations. So this is basically the generative model that we use here. So for this example, this is a bird call, and by following this graph, now you can remix this bird call and create other variations on top of that. So the structure itself is the factor oracle string matching algorithm that finds suffix links, and by navigating the suffix links, basically create a remix. Now, given this ability to form structures and understand repetitions, which is in some sense what makes sense of music, and the idea that the time flow and the information passing from past to the future is actually captured in a concept that is pretty powerful and became popular in music analysis, which is called musical information dynamics. So the whole idea that a performer creates expectations and the listener, or actually the performer, by providing his musical material, creates expectations in the listener's mind, and by manipulating the validation violations of these expectations, actually this is what emerges as the musical structure. So this gives us a predictive view of musical listening, and the fact of anticipation is actually modeled by something called information rate, the IR expression here, which is the mutual information between the past and the next instance of the musical signal. Now, depending on the features that we're using, of course, we need to quantize them. This is the Q. This is described more at length in the paper. We get different motives that are detected by this VMO mechanism. And it really depends on the style. So this one is a classical musical example by Telemann, and this is a Far Eastern Chinese dongxiao music. And you can see the granularity of this musical elements changes very much depending on the sense of what is the musical meaning or expression is built upon. So the quantization portion and finding the phrases are really critical to extracting the structure of the musical signal. Another aspect of this work is that the system can be queried. You can actually provide an input signal and we'll try to find an approximate path that best approximate an input. So let's see how it works for video improvisation. Here we have the Hulk as the query, and the Spider-Man is actually modeled as a graph. Now it tries to imitate the Hulk. So the movements are based really on recombining video frames after the analysis by VMO. So some of the problems with generative modeling is that a lot of the results are tend to be loopy. They tend to replicate. Also, the quality is not very good. So in this example, that another part of our research where we use sample RNN for videos, you can see how the frames start repeating themselves, because this is basically a very nice path. It's the maximum likelihood kind of solution that the system finds. The same is with this percussion example generated by CNN. So to overcome these methods, we actually propose a certain paradigm where we have the latent encoding with a lossy representation that has to be then quantized and symbolized to find longer patterns. And we analyze them using predictive information to build policy rewards. So our basic model actually assumes that there is a flow of time, which is then encoded in some latent space in our mind or in the computer mind. And by going through this, we actually have a step of decoding or encoding and decoding that actually provides a lossy view of the information that passes over time. This time analysis is done, for instance, using the VMO. And our goal is actually to best predict the future based on a compressed encoded representation of the past. This actually creates these two contrasting minimization of this relation and maximization of this relation, which gives us a predictive information bottleneck setup. Of course, we can use also other representations. We're also exploring BQVE, which is a vector quantized variational autoencoding. When it's applied for music, we're using a jukebox, which is an OpenAI project that uses the same technique for audio. Now, if we want to deal with multiple voices, we can actually extend this by a concept of transfer entropy. And we know that, or we have shown this as a recent result in another work, that you can actually estimate the transfer of information between two processes by accounting for their information flow in time for each one of the voices, the joint information flow of the aggregate, and the mutual information between each one of the flows averaged over the whole signal. So this gives us kind of a glimpse into the structure. And also another note, which is explained in the paper, is that by reducing the representation, by having bit allocation that kind of reduces the size of the encoding in the latent space, you can actually discover more sometimes a higher correspondence between voices than actually using a higher resolution representation. So these are the rates, and these are the two voices to be examined. And you can see that the peaks are actually occurring in some mid-range of the rates. So if we want to use reinforcement learning as our paradigm, this solves the problems of long-term discounted rewards by providing a representation of states, which is a sequence of notes played so far, and the rewards become the motives. So actually, VMO builds the motives. We have seen this in the previous slides. And if the generative mechanism is managing to generate the corresponding set of motives, it actually is reinforced positively. Now, since music has multiple ways or multiple options of generating according to the features, according to basically almost like multiple heads that have multiple representations working parallel, we propose to use the option keyboard. So we have a reward for the composer based on how well it actually predicts whatever the goal, the surrounding or the music that comes from the musicians. The musician in his turn also probably does something of a similar. And then with multiple options, with the option keyboard, we actually propose an architecture that controls or optimally weights the different rewards and chooses which models should be used to create the optimal improvisation. So as a summary, we propose a new paradigm of co-creativity where the framework is creating the symbiotic interaction between humans and digital entities, where the philosophical aspect is that co-creativity is actually emerging from continuous interaction between humans and digital systems. And there is this joint learning that happens that based on the feedback that creates this symbiotic interaction. So as the last quote, I would bring up Abraham Moles, who actually expressed this idea of communication as the essence of creativity. And what he says is really forms do not exist in themselves. They are only perceived, they are products of the receiver applied to the message. So thank you for your attention, and I'll open this up for questions.